All right. Now, equation C um, tells you how you combine your model prediction, right, and your sensor reading, right? Because you can see it over here, x hat k is your previous estimate, okay? The previous estimate, uh, and this is the observation coming from the sensor, all right? So, um, in fact, if I go back a little bit, uh, I can show it to you, right? So it's actually coming from this equation, state update, right? It's uh, x hat minus k plus 1. You can see the previous um, equation over here, number 1. This is a predicted value, right? Predicted value. And z k plus 1 is the sensor. So here you combine the two together. Okay, you combine the two together, uh, and I think we went through this process uh, to find out how these two gains or weights are related to each other, because you have to take the previous estimate, okay, uh, and also the sensor, right? How you can combine these two together, right? I think it's good if you can use put over here um, the predicted state, that is x hat minus k plus 1 over here, right? If you use this one over here, so it is the predicted value right now. Okay, I will make that correction. So this is one option, right? You know your position from the model without any sensors. And on the other hand, you have the sensor telling you this is your position, okay, at k plus 1. Now remember, k plus 1 is the present position. This is the previous one. K is the previous one. Okay. In fact, this has to be x hat minus k plus 1. So from your previous position, you use your model to calculate the present position, right? And it is the predicted present position. Okay. So now you use two gains. One is k dash, the other one is k, right? These are weighting factors, right? Say, for example, k dash is 0.3. In that case, this is 0.7, something like that. Okay, you take 30% from here, 70% from the other, right? Whichever is more reliable, you take a bigger portion of that and combine them together and say this is my best estimate, right? Okay, so this is pretty much what we do when we are not really sure about any of these measurements, right? And every measurement has a little error. Now, how do we estimate the value, right? You can say, okay, go for the sensor which has the smallest error, which is not very accurate, because other sensors are also accurate, not as accurate as this particular sensor, but maybe other sensors also are meaningful, right? They're telling something meaningful. So you have to combine these things together. And that is the best estimate. Okay, right. So this is what we do over here. Now, when you go ahead with that kind of prediction, that is combination of two things, model predicted value and the sensor reading, right? You are generating an error here also. Every process has an error. Kalman filter is no exception. It also has an error. Now we want to um, reduce this error, right, to 0. Right? There's one sweet spot between these two, k dash and k, which makes the error 0. Right? So we went ahead with this process last week and eventually figured out when the Kalman filter prediction is unbiased or 0 error, right? Which means you have the actual value, you have the filter estimate, Kalman filter. And the difference is I won't say exactly 0. Expected value of the error is 0. Right? This is stochastic thing, right? Sample thing. You get so many samples, and when you average it out, it becomes 0. But there can be an error at every moment of time. But if you average it out, it's 0. That is what we call expected value is 0. So please understand that point, okay? Kalman filter predicted value and the actual value can have a difference. It's sometimes positive, sometimes negative. It flips back and forth, right? But if you average it out, it goes to 0. So when you clamp this equation, saying that we want to have the Kalman filter estimate to have 0 expected error, okay, then you will eventually find this relationship. If you want to have unbiased estimate, this is the relationship between k and k dash. See, one side is k dash, the other one is k. All right. Now we include this as a constraint into a Kalman filter, so that Kalman filter becomes 0 bias, which means at the filter estimate and the actual value, right? There is an error, sometimes positive, sometimes negative, but you add them together, errors, and divide by the number of samples. Okay, addition becomes 0, right? So it is 0 mean. Okay. Now, next thing we want to do in the Kalman filter is, now we have a 0 mean error estimate, but we want to have the variance as minimum as possible. Okay. So having 0 mean estimate is of no use if the variance is too large, because then your estimate can be very different from the actual, maybe too far into the positive side or too far into the negative side every time. So you can't use this sensor. But if you look at the average error, it's 0, because this is flipping back and forth by a huge amount. It's useless estimate, but mean error is 0. To avoid that kind of situation, what we want to do is to minimize the variance so that it's just flipping around the actual value. The estimate is just moving around the actual value, right, within a very narrow margin. So we want to reduce the variance. Okay, right. So when you have an error, let's say e k plus 1, this is error. But the difference between the actual value and the filter, Kalman filter prediction, that is x hat minus x. Okay, so here you can see that error, x hat minus x, right? You can have timestamp k plus 1 or k, right? At any moment of time, what is the difference between Kalman filter estimate, that is the hat, and the actual value? So this is distribution, right? Error is sometimes, as I said, positive, negative, big and small, like that, right? You get different values for error. But if you want to see the variance, I think you remember last week we discussed about what is the mean, how to calculate mean, variance, covariance, and correlation coefficient, right? If you have forgotten that, you will not understand what I'm saying today, right? So when you have this kind of error that is changing all the time, you want to get the expected value of the error to see the range over what kind of range it changes, right? So in linear algebra, what we do is that we write it like this: expected value of E k plus 1, E transpose k plus 1. So um, the vehicle example I explained to you has only one state, the position, right? But generally, plants have many states, x1, x2, x3, like that. So each state, for each state, Kalman filter has a predicted value. So state 1, state 2, state 3. So it's a vector. Okay, this is a vector equation. There are a number of elements in that vector at the same k plus 1 time. So you put that vector and the transpose of it. So it's like this vector and the column. You multiply uh, element wise and it becomes like this, right? So sigma 1 square is actually error square, right, of the first state variable, right? And then you have epsilon 2 square, that is for the second state variable, third, fourth, fifth, and so on. Each and every state has an error, and this is uh, the covariance matrix. Okay, sigma is the standard deviation, square of that is the variance. But generally we say covariance because this can be the same signal or different signals, right? Here, the variance is calculated only with respect to that particular state, x1 and x2. We are not actually combining x1, x2 together. Then it becomes actually covariance matrix. So, that is P, that is the covariance matrix. Okay. Now, if these numbers are big, is a big covariance. If the numbers are small, it's a small covariance, right? So how big or how small is the issue now? We want to reduce it as much as possible, okay? Because it's a multi-state thing, right? We want to add them together, sigma 1, sigma 2, and all. So this is all squares. So therefore, they're not canceling out each other like positive, negative. You add them together. When you add the diagonal elements of a matrix, we call it trace. Trace of pk plus 1 is actually sigma 1 square plus sigma 2 square and so on. And you want to minimize it. Now see how elegant this process is. Rudolf Kalman has lined it up. Maybe it took a lot of time of his, right, to figure it out. Now it's somewhat easier for us to follow his footsteps. But the first person who walks this one, right? Imagine the thinking. So you get the trace of that diagonal element matrix and try to minimize it. So you are actually minimizing all these variances of the errors. Okay. And in the minimization process, we expect to find the Kalman gain. So earlier, we found the relationship between K dash and K, right? It's just the relationship, but we don't know the exact values of either of the two. So you need to find out either K dash or K. Then you can calculate the other one using this relationship and then put it in the state update equation and get the update. But right now, we only know that how these two elements are related to each other, K dash and K. We don't know exact value of any of these two parameters. That's why we try to minimize the variance and in the process, find out the value for K. Okay. So we first write down the prior estimate error, prior, that is E minus, okay? So the draft, not the final corrected one. So we write it down as x hat k plus 1 minus xk plus 1, but with this minus, which means is the predicted state. This is the actual state without any head. It is the actual state, right, of the system. This is the estimate of the Kalman filter. Now you can write x hat minus k plus 1 as this from equation number 1, state transition, right? So minus, this is the plant. So you have state transition times xk. Xk is the actual state, whereas this is the Kalman filter estimate. Okay. Plus you add the process error, unmodeled dynamics or disturbance, whatever it is, right? Remember, we assume here this W to be Gaussian distributed noise kind of thing. Okay. Then you get the state transition matrix out, and you generate x at k minus xk. Now, this looks like t, but this is actually k. Okay. Now this is x hat k minus xk means error e k. So this is the error in the previous time step. Error, final error in the previous step. On the left-hand side, it is the error now, the present state, present time rather, but it is not the final corrected error, but predicted error. So every step, you have the predicted error and the corrected error. And in this equation, you take the corrected error of previous state and you calculate the predicted error of the present state, okay, present time. So therefore, this is your the latest equation for predicted error at k plus 1, right? Now, from error to the covariance, right? Error to the covariance, we look at it earlier, right? You want to get the expected value of the left-hand side and the right-hand side. So when you get the expected value of the error variance, right, we write it as P. P is the variance, right? K plus 1. And because this is predicted, variance is also predicted variance. Now, when you get the variance of something like this, where EK is preceded by a matrix over here, right? A state transition matrix. When you get the expected value, this is how you write it. Okay. So this is in linear algebra and statistics, you may have learned that one. So this qualifier of the variable ek, it comes over here in front of the expected value and after the expected value as transpose, and in the middle is the expected value of error squares. So we write down ek transpose, or error, the row and the vector, right? Column vector. So you multiply element wise, error squares, and then you add them together, right? And divide by number of elements like that. So expected value of error squares, okay? And on the right hand, plus the second term on the right hand side is the process noise or unmodeled dynamics in the plant, okay? The expected value of this one. Again, this is kind of noise. You have to get the squares and add them together and divide by number of elements, and that is the variance, okay? So what is the expected value of that? We give a symbol for that one, right? That is capital Q, K plus 1. So we assume that we know capital Q, K plus 1, otherwise Kalman filter cannot operate, okay? So this is equation number 2. There, to go back to the Kalman filter. 5 equations, right? This is equation number 2. This one. Okay. Now, step number 3, we want to calculate the Kalman gain. For that, we start with equation C in page 13. If you go back, this is page 18, right? If you go back to page 13, C, this one. This is the first equation we discussed today. How you combine the previous estimate, the predicted value from the model and the observation. Now, how would you combine them together, right? This equation. And also we are using equation D from page 15, right? Equation D, this one from page 15. So this is how K dash and K are related to each other, right? So you can actually put this value K dash K plus 1 into this one, equation C. You can see K dash K plus 1 over here. You can put this one, K dash K plus 1, this whole thing into here, right? So that is what's happening over here, right? So now we don't have K dash term. We have got it substituted, right, with this expression. Now, when we do that, the property of zero bias, right, is now here in this equation. Because this K dash and K relationship, right, we found is based on zero bias. So the Kalman filter estimate and the true value of the state, right, as I said, now has zero mean error. Okay, it doesn't mean zero error. It's zero mean error. Remember that. Okay, at every moment of time there can be an error, but the mean error is zero. So this is the equation which has that property. Now, what is the error at K plus 1? This is the estimate of the Kalman filter. The filter says, okay, this is your state at K plus 1, right? Now, what is the error? Error is the Kalman filter estimate minus actual state. So I get this entire thing over here and put a minus xk plus 1. This is the actual value. This is the predicted value by the Kalman filter. This is the error. Okay. Then I do some manipulations over here. You can see I minus kh x hat k plus 1. This is the predicted value coming from previous state to the present value, right? Predicted value at k plus 1 by Kalman filter. Plus you have k over here. Now you don't have k dash. It's already gone. Then you have zk plus 1. So what is z? Z is the sensor reading, right? This is the second equation of state model, state space model, right? Remember x dot equals ax plus bu, y equals cz. This y is actually z in Kalman filter, right? It is actually y output, but we give this z symbol, right? Most of the literature refer to Kalman filter uses z in place of y, okay? So it is actually a linear combination of states, right? Y equals Cx. You remember that, right? Now C is H here. So that is why this Z is replaced by Hx. But not only that, there is this V, that is the sensor noise. Now we consider noise part also in the sensors. Okay. And then the last term minus xk plus 1. Now we move on to this level where you can see you expand this bracket, and therefore you get x hat minus k plus 1 minus kh x hat minus k plus 1, the second term, plus first term over here, plus second term minus k xk plus 1. Then you can figure out x hat minus k plus 1 over here and xk plus 1 over here. So combine these two together up front over here. Okay, minus, you can see k and h, and then x hat minus k plus 1, and also there's xk plus 1 with the same terms in front. So you get this kh, right, out of these two terms and write it down as x hat minus k plus 1 minus xk plus 1. All right, so this is a nice rearrangement. So we have got 4 terms already, and there's one remaining, that is k plus 1, v k plus 1. That is the sensor noise. Now you can see that both of these terms, right, they have this common term, x hat minus k plus 1 minus xk plus 1. Same over here. You combine these two together and say, from the first one, you get the identity matrix minus k and h, okay, kh, plus k times v k plus 1. Now, what is in the bracket here? X hat minus k plus 1 minus xk plus 1. This is the Kalman filter predicted state minus actual state. So this is also an error, but it is the predicted error. That is why we put a minus. Okay, so on the left-hand side is the corrected error. Now see how we get the predicted error and we correct it. This is the correction equation for error. So in this slide, what is up front is actually the last equation, the previous slide, right? And then we calculate the expected value of the error. Now you have an expression for the error, but thing is, this is like a stochastic variable, right? It changes positive, negative all the time. So when you have that kind of signal, right, you use to statistics and probability, okay? Because it's not a definite thing, right? It's always changing around a mean within a variance, okay? So therefore, handling that kind of signals is always with the expected value. So what do we expect as the value over a period of time, right? That is the only meaningful thing in this kind of signals, right? Because simply because every moment, whatever you get, you cannot believe 100%. It's a changing thing, back and forth, back and forth. So the only meaning thing is that, okay, observe it for some time and get the average or mean value and also get the variance. That is the only meaningful way of describing that kind of signal as stochastic signal. Okay, right. So now we understand. So let's get ek plus 1, which is, of course, of no use as it is. So we can put it into this format, right? The ek vector and the transpose, multiply element wise, get the expected value. Then it makes sense. Okay. So when you do that on the left-hand side, what's happening on the right-hand side? So I minus kh, right? So is a qualifier or the the multiply of actual signal, E minus K plus 1. So we get the expected value of E minus K plus 1 like that. And in front of that, we have I minus KH. So it goes the front and then back, right, in this format. Plus the expected value of the squares of sensor noise, right? Maybe you can have more than one sensor. So therefore, this goes like as a vector, V K plus 1 and V K plus 1 transpose, right? If you have more than one sensor, they are vectors. So you get the expected value, right? That is noise squares, add them together and divide by number of samples. So the left-hand side is actually the covariance, all right, of the error. This is E K plus 1, error at K plus 1. There's no negative sign over here, right? This is the corrected one. This is what predict the Kalman filter outputs, right? As this is my state prediction, and this is the variance, okay? So it produces this P matrix. So again, because we are dealing with more than one state variable, okay? So these are all matrices. Remember that, okay? In some examples, you will have only one variable. In that case, it's just variance of that signal. But if you think of a state a vector of n variables, so it becomes n variable thing. So when you have this n by n matrix, this is your covariance matrix. All right. And if the state variables are not related to each other, you have the variance right in the diagonal. All the other elements are zero, right? But if they are related in some way, you will see covariance around the either side of the diagonal of the matrix. We will do an example, then you get some idea, right, of how this really works. Most of this very complicated, looks like very complicated mathematics will become like not something that is in your way when you get grip on actual example, right? Then you understand how you use these equations. You will see it easy, okay? But if you follow the mathematics, sometimes it's not that easy. Right, okay, on the right-hand side, we have E minus K plus 1, right? Covariance matrix of that one. We put a symbol for that P negative, right? Minus. There is a predicted covariance matrix. And of course, you need to have this I minus K H transpose. I missed it over here. Plus this one. You can see it over here. This is the sensor noise. Sensor noise is V K plus 1. It's again a stochastic variable, meaningless unless you average it out and give it a mean or the variance, mean and variance. These are the only two attributes of stochastic signals, right? The basic attributes of a stochastic signal that help us to understand the nature of the signal, okay? So if you want to get the covariance of the noise, okay, you have to get the noise values. If it is zero mean, we assume it to be zero mean. All of these sensor noise elements squares and add them together with the root of that. And that is the standard deviation, okay? But without getting the square root, it is the variance. We say covariance if you have more than one and they are cross-correlated, okay? So that matrix we give the name R of the sensor. All right. If it is just one sensor, one reading, it is just a number, right? Not even a vector, right? Not to mention about being. matrix. Okay. Generally, general mathematical treatment uses it as a matrix, covariance matrix of the sensor. But if it's just one sensor giving one reading, it is just a number. Okay, one element matrix. So because this notation is bit uh, uh, occluded by this subscript k plus 1, we know they are all k plus 1, so we get rid of that and write it down in a much simpler format like that. So this equation over here is exactly this equation E, right, without k plus 1 subscript. So it makes us feel better, okay? So it is I minus kh, then P minus I minus kh transpose plus kr k transpose. Then this is exactly the same equation. I don't know why I wrote it. Anyway, then you multiply this one, you get this line, right? Like over here. Now, what do we need to do right now? Or why we calculated? Why did we calculate the covariance matrix in the first place? Because we wanted to minimize the covariance. Right? Now we have the covariance matrix. How do we minimize it? Get the diagonal elements, right? That is the trace basically, right? Then we know how big or small the covariance is, right? This is error covariance, not anything else. It's error covariance, okay? So get the trace on the left-hand side and also right-hand side. When you do the right-hand side, you get trace P negative minus 2 times trace KHP minus plus trace of so I think you can add these two together. This cancels out, okay? KHP minus, KHP minus. Yeah, so you can add these two together by transposing this one, right? They will add to the same value. And the third one, trace of this one plus trace of KRK transpose. All right. The second element and third element, they are the same. They have the same value. So that's why we put minus 2 times. Okay. And this is the size of the covariance matrix. Sum of all the diagonal elements. Now we want to minimize it, right? Minimization needs an independent variable, right? You can minimize a function by changing another variable, okay? So here, what is that variable or parameter that we have that we can use for this minimization? Of course, it is the Kalman gain. It is the Kalman gain. So we want to find out with respect to the Kalman gain, what is the minimum variance? So see how elegant this concept is. We first calculated the Kalman gain, right? And then the relationship between measurement and the state prediction, right? And then we use that one to find out a relationship for the Kalman gain. And we now use the Kalman gain to minimize the variance of the error, okay? So let's get the partial derivative of the trace with respect to K. Then on the right-hand side, we have trace P minus of the negative with respect to K and minus 2 trace KHP minus with respect to K plus trace KHP minus H transpose times K transpose with respect to K. and then finally trace kr k transpose with respect to k. Okay, all partial derivatives with respect to k. Now, if you look at the first term on the right hand side, the value is 0, assuming minimum covariance in prior estimate. Now, if we assume, okay, we had the minimum covariance previous step, now we are going to the next step, okay, like mathematical induction, right? If you want to prove something, you can assume that it was true in the previous step, and you can use that one to verify that it is true for this state as well, mathematical induction, okay? So this is exactly that. You have the right to assume that you had the minimum error covariance in the previous step. Okay, so this is exactly that one. P minus means the predicted error covariance with respect to k, right? That is 0, right? If we assume that covariance was minimum with respect to k, so therefore you are at the minimum, your rate of change is 0. Therefore, the first term on the right hand side is 0. Minus 2 times is trace. For that, there's a identity in linear algebra. What is that? If you get a trace of product of two matrices A and C, right? Trace AC, and then you differentiate it with respect to this matrix A. Remember the first day, we look at how scalars are differentiated with respect to a matrix and all that, right? So this is one of these identities. So if you have A times C, right, and you get the trace is a scalar, right? Trace is the summation of the diagonal elements. It's a scalar, and you differentiate with respect to the matrix A. The answer is C transpose. Now, if you go up and see whether you have this kind of thing over here, well, what you have is KHP negative with respect to K. Right? It's somewhat similar to this one. Trace AC over A. Now, what is A over here? A is like K. What is C? C is HP negative. HP negative. So therefore, the answer should be C transpose, which is HP minus transpose. HP minus transpose. Okay. So that is the second term. What about the third term? So there's another identity over here. If you have a trace of this expression ABA transpose, ABA transpose, and you differentiate with respect to A, right? The answer is 2AB, right? You can prove this later at home. I'll put some numbers for AB matrices and differentiate with respect to A and see what you get. Now, this is exactly that. A, B, A transpose. Okay. Here also the same. A, B, A transpose. Now, A is actually K over here. Anyway, you are differentiating with respect to K, right? So therefore, in this, to be aligned with these identities, A should be K. So the answer is 2AB. So therefore, the answer here should be 2AB. 2 times, this is A, this is B. Here, this is A, this is B. Okay? So like that. Then we can write down the right-hand side. Trace partially differentiated with respect to Kalman gain is this. And this has to be 0. Okay, this has to be 0. We set it to 0 and find out the Kalman gain, exact Kalman gain, right? To minimize the error to 0, mean error to 0, and minimize the variance. So when you set this to 0, right, as a result of partial differentiation with respect to Kalman gain, the result also has Kalman gain. So when you set it to 0, you can find an expression for Kalman gain, which is this one, right? Kalman gain is P minus transpose HP minus H transpose plus R, all thing inverse, right? So this equation will calculate Kalman gain so that the error estimate will be both zero mean and minimum variance. So remember these two properties of Kalman filter: zero mean error and minimum variance. Okay, so that is equation number 3. Is everything clear up to now? All right, so let's move forward to step 4. Step 4 is this. From the equation C earlier, with substitution for k dash k plus 1 from D, right? You can write it down like this. I think you remember this equation. The state prediction, right? Kalman filter estimate at k plus 1 is coming from this portion times x hat k, right? This whole thing is actually x hat minus k plus 1. This is the predicted value. This is what I said earlier, right? Predicted value from the previous state to present state only by using the state transition without considering the unmodeled dynamics of the plant or the sensor part, right? Disregarding all of these things, you just blindly look at your future, right? Um, that is somewhat meaningful, but not precise. So you get this part of that, and then your sensor reading is at k plus 1, this part of that. So combination of the two. So that is step 4, right? Step 5 is update error covariance of the probabilistic estimate. So if you put equation number 3 onto equation E, you can obtain this one. This is given without proof actually, right? So just remember that one. Equation number 3, you can pedal back to this one. This is a Kalman gain, right? And if you put it into equation E, right? Earlier we found that one, this one, right? Replace this Kalman gain, k plus 1 here and here, and you can actually show this relationship, that pk plus 1 error covariance, right? The error covariance means the filter estimate, right? How much it varies around the actual state, right? This variance is finally this I minus kh, p minus k plus 1. So predicted error covariance on the right hand side, and you multiply it with this one, the result is corrected error covariance at time k plus 1. So that's equation number 5 in the Kalman filter, the last equation. Finally, you can draw the Kalman filter like this. It's a single block, right? You have to give x hat k, the previous estimate, all right? And it produces the next state, x hat k plus 1, okay? But you need to give state transition matrix, capital phi, and output matrix or vector H, and you have to give a Q, that is process noise covariance, unmodeled dynamics, whatever it is, and the noise covariance of the sensor. That's all, right? And this is recurrent algorithm, so that once you calculate your estimate, you have to read it back so that you can calculate the next state. It goes on and on and on. Okay. All right. Now I have this example to you. I try to work it out. I will explain before we get a little break. Describe the two basic properties of Kalman filter. You know that it is zero mean estimate and minimum covariance. Okay, those are the two basic properties of Kalman filter. Write down the Kalman filter algorithm describing each of steps. Right, you can do that. Don't do it right now. You can practice it later. Okay, basically rewriting the notes because everything is clearly written already. You can write it down your own way, okay, without copying. See, this is actually the problem. A spacecraft is accelerated by burst of gas ejected by its reaction control thrusters. Okay, so there's a spacecraft in the orbit. Okay, you have to visualize this process first. Okay, position, velocity, and acceleration of the spacecraft. So it's moving, right? Here and there. There's a position, there's a velocity, there's acceleration. Are denoted by pk, p dot k, and ak. Position, velocity, acceleration. I could have used pva, position, velocity, acceleration. For some reason, I have used p dot for velocity and then a for acceleration. Sorry about that. First part, write expressions for PEK plus 1. So can you write down a model equation to calculate PEK plus 1 and P dot K plus 1, velocity, next step, velocity, and show that the state space model of the spacecraft is this one. The first part is actually developing the state space model of the spacecraft, okay? Where T is the sampling interval. After that, it says an anomaly happens in the reaction control system. So these thrusters are used to keep it in position. If it drifts this way, the thruster is actuated to bring it back, right? But there's an anomaly so that now these thrusters are issuing, right, burst of gas here and there so that it's moving all over the place, okay? So this is unmodeled dynamics. It was not there earlier. Now there is this dynamics, okay? So we cannot neglect that one. We have to consider that gas burst and therefore the resulting motion of the spacecraft and predict where it goes as a result of these random gas bursts, okay? Now, this random burst of gas that result in zero mean random acceleration. So because of that, there's a zero mean random acceleration. There's acceleration this way, that way. That is why we call it zero mean. It's not continuously drifting this way, but it's moving back and forth kind of thing, right? So if you look at the acceleration and average it out, it becomes zero. It's a zero mean acceleration. But there's a variance, there's a standard deviation of 2 meters per second square. That is how big the variance is, right? It's sometimes positive, sometimes negative. Therefore, mean is zero, but it varies around zero by this much. Show that the process noise random acceleration covariance matrix of the system is this one, right? The first two parts are like that. Try to figure that out, right? Within the break, we'll take about 15 minutes so that you can take about 5 minutes for break and the 10 minutes for these two parts of the question, right? Any questions about this assignment? Is everything clear? Okay. Now let me explain it to you again. The first equation over here is how the position changes from k to k plus 1. And we know it is present position times velocity times time plus half acceleration times t square. And how the velocity changes from k to k plus 1 is in the second equation. That is p dot k plus 1 is equal to p dot k, present velocity times plus acceleration times time. And then you can write down these two equations, one for position update and the other one is velocity update as in matrix form or state space model. Then on the left hand side, you get position update. On the right hand side, you get the present position. Okay. So from the first equation, you get 1 pk and t times p dot k. So it is 1t, the first row. And in the second equation, you don't have any pk, but there's 1 p dot k. So it is 0, 1 in the second row. Plus, you have disturbing terms from the acceleration in both these equations. First one, half t square times acceleration. Second one, just t times acceleration. So you write it down t square over 2 and t as a column times acceleration. So that is the state space model of the plant. Second part is how to calculate the process covariance matrix, right? That is basically coming from this one. This is the process noise. Okay, when the spacecraft is in orbit, it's not supposed to move anywhere. There's no random acceleration, right? Because of this malfunction in the control thrusters, it's now moving here and there. So that is the process noise. It was not there, but now it is there, right? So with the knowledge of the noise part, process noise part, right? You saw in the Kalman filter derivation, if you know the error, you can get the error square and the expected value of the error, okay? Error square. So that is what is called the covariance. So here is, we follow the same process, right? So we give it a name like W, right? That is the process noise. Now it has two elements, right? Because it's to a state system. So the first part is actually AKT square by 2, and the second element is AKT. So now these accelerations are random. So AK is random. So therefore, this is a random disturbance. Now, if you want to get the covariance of this one, you want to get the squares of these and add them together, divide by number of samples, and that is the variance. Okay, so you can write it down as this. The variance of W1, the first one is actually sigma A square, right? T to the 4 over 4, because you want to get the square. In the example, it is given that the process noise is related to acceleration, random acceleration. And this random acceleration has its standard deviation or variance. It's a known value. It is given in the example. So if it is the standard deviation that is given or the variance that is given, right, or the acceleration, right, it doesn't matter. We can write it over here, right? Sigma A square goes to, it represents the variance of acceleration. But here in the model, the noise is not only the acceleration, but it is multiplied with t square over 2 in the first equation and by t in the second equation. So therefore, the covariance matrix of the process noise should be calculated using the covariance of the acceleration or the standard deviation of the acceleration, random acceleration, which is sigma a, which is given. So it is sigma a square, that is the variance of the acceleration, times t to the 4 over 4. Get the squares, okay, of this one. Second one, sigma a square t square, because it's just t in the sigma. If you see the stochastic variable in one of the equations, when you want to calculate the variance, you get the square of it. Just simple as that, okay? Now you have the two variances for W1 and W, this should be W2, second one, I will make that correction. Now, the covariance matrix in a 2 by 2 matrix is like this. The covariance between W1 and W1 here, W1 and W2 here, W2 and W1 here, W2 and W2 over here. So here we assume there's no cross correlation, right? So therefore we, in fact, here there is a cross correlation, right? Because position and velocity, acceleration, they are linked together, right? They're moving together. So with the known variances, right, for W1 and W2, you can calculate the covariance between W and W2 in this format, right? You can see it over here. At the top left element, the covariance of W1 is actually variance of W1 square and the square root. So eventually it becomes t to the 4 over 4, right? This variance itself, variance square and then a square root means the same variance, right? The same term comes over here. And the right bottom one, right, the covariance of W2 is actually the variance itself, okay? So W sigma a square t square, that comes over here. Sigma a square is a common term, so I take it out of the matrix. Now here, top right element is variance of W1 times variance of W2. You multiply the two together and then get the square. So when you do that, it will be t to the 3 over 2 here and here. All right. So this is your process covariance matrix. All right. Then any questions about that? So we'll go back to the question, right? So this is the covariance matrix given, and we have derived that. Let's move on to the next section, that is 3. It says position of the spacecraft is measured by the position gyro as zk equals pk plus vk. There you are. There's a sensor to measure the position, but there's a noise in the sensor, vk, right? So where vk is the zero mean gyro sensor noise, zero mean noise. So it adds random value to the actual position and tells, okay, this is the reading. Standard deviation is about 1 meter. Okay, so when you measure the position, don't worry about this gyro thing. Usually gyros are used to measure the angles, but now it's like 1 meter distance. There's a little problem there. So maybe we can remove this position, the gyro term with position sense. All right. Okay. So before the anomaly happened, the spacecraft was on stable orbit at equilibrium point, k equals 0. So you can assume it to be located at 0 point, whatever it is, right, at k equals 0. Then you got this anomaly and the thrusters are now emitting gas burst here and there. And at the first two instants, followed by the anomaly, that is k equals 1 and k equals 2. So you go from 0 to 1 to 2, right? Position was measured by the position sensor as 0.1 meter and minus 0.2 meter. You can see the randomness here, right? The first time step, the measurement from the sensor is 0.1 meter. And the next moment it says 0.2 meters, negative direction. Okay. Now you are asked to use Kalman filter and estimate the position and velocity of the spacecraft at these two instances, right? Can you use a Kalman filter and estimate the position, right, at k equals 1 and k equals 2? So that is the question asked. Okay. So you are given the sensor noise standard deviation of the sensor noise, that is about 1 meter. Okay. So right. So this is how we solve this problem. We bring in a Kalman filter here, right? This is how the filter works. First, you have the initial state, 0, 0. We will assume it to be 0, 0, which means position 0, velocity 0, right? So I take this as um, x hat 0. Time is 0. X hat means the Kalman filter estimate. Because I don't have anything at this moment, time 0, I can assume anything. Even for the filter, you start with some value. You must have some value, whether it is right or wrong, it is separate matter. So by default, we start with 0, unless we have some idea of the state, right? So we start the Kalman filter with 0, 0. And I also assume the same value for x hat 1, that is time step 1. Okay. So because I don't have any information to say anything otherwise, this filter will correct itself, right, as we go, so that initial values are not that important. This is kind of learning output, right? So don't worry too much about assuming initial values, right? You figure out what is happening and what you know, and then uh, start with something really meaningful, right? But if you don't know anything, then you can start simply with 0, 0. So then we calculate the initial error covariance matrix, that is P1 negative, P1 negative, right? And I assume it to be the covariance matrix I have already derived, which is this one. Remember, previously we derived that one. And also, we are given that standard deviation of the acceleration is 2 meters per second square. That was given. That was the standard deviation of the random accelerations produced by these gas thrusters. So it is 2 meters per second square, that is sigma A. So it becomes sigma A square over here, that is 4 times this one. And also we are given the time stamp for sampling interval here is 1 second. So therefore capital T is 1 second. So it will be 1 over 4, 1 over 2, 1 over 2, 1. So all of a sudden, when you put the numbers together, right, now you have a known Q matrix, process covariance matrix, right? P1 negative. So this is the predicted covariance, error covariance matrix. And if you look at the state space model, this one, when capital T sampling interval is 1 second, this is 1, 1, 0, 1. So this is the state transition matrix, right? State transition matrix is also known. So you can write that also. Then the output matrix, H, right? What is H? Well, H is a row vector, right? Which will have ones in the positions of the measured states and zeros in the positions of unmeasured states. So we have two states here, position and velocity. And this sensor measures only the position. So therefore 1 over here, 0 there, right? And it is also said that the sensor has some noise, standard deviation of 1. Is it 1 or 0.1? If I go back to the question, 1 meter, right? Look at over here. So sensor noise with standard deviation of 1 meter. Okay. So therefore, sensor noise covariance is standard deviation square. You know that, right? When you are given standard deviation, square it, and then you get the covariance, right? So it is 1 square, which is 1. All right. So you know a lot of things now. State transition matrix, that is capital Phi, and the output vector H, R, which is sensor noise covariance, and Q, process noise covariance. Okay, and also P1 minus we assume to be equal to Q because we have no other criteria to determine that, because this is the first step, very first step, right? You have to assume something. Okay. Without these things, you cannot start the engine, the recursive process. That's why. Okay, now you are at k equals 1. So when you move from 0 to 1, right, you have to calculate the Kalman gain. This is the equation for Kalman gain, right? From the algorithm, you don't have to remember it. You can take it, right, as it is. That is the predicted error covariance, right, at k equals 1, present moment, and also output matrix, the vector transpose, and within bracket h1 p1 uh, predicted h1 transpose plus r1, all thing inverse. Okay, this is the Kalman gain that will have zero mean and minimum variance estimate. Now put the numbers in. we assume P1 had to be the process covariance matrix itself, that is 1, 2, 2, 4. And the output vector is 1, 0. So when you get the transpose, it becomes 1, 0 column. And then H1, P1 minus H1 transpose. These are the vectors and matrices plus R1, the sensor noise covariance is just 1. We have derived it earlier. Now, when you multiply all these things, this becomes just a scalar. Value is 2. And inverse of a matrix. And the matrix is just one single element matrix is actually reciprocal. Okay. So this 2 becomes 1 over 2 inverse. Okay. So then the result is 0.51. So this is the Kalman gain. This is a Kalman gain. So it's not just a gain, it's a vector because you have position and velocity. Kalman filter predicts both position and velocity. Okay. Even though you measure only one variable, that is position, the filter knows the dynamics and also the noise variances, and then it can estimate all of the state variables. Then we move on to the prediction, right? Actually, correction of the state. Earlier, we got the predicted value, right, which is 0, 0, because we didn't have any other way to estimate it. But now we can actually put the process to calculate x1 hat. Okay, when k equals 1, what is the best estimate by the Kalman filter? So this is the equation for that, x1 hat minus predicted value plus Kalman filter calculated for that time step times z1, that is the measurement, minus h1 x1 minus hat. This is the predicted state. This is the sensor measurement. And if you look at the question, it says, okay, the first reading of the position was 0.1 meter. It says, okay, the spacecraft has been deflected by 1 meter. That was the first reading. So you put it over here. H1 is 1, 0, and x1 minus hat is 0, 0. We assume it initially. Kalman gain has already been calculated, and this is also 0, 0, because initially it is 0, 0. Now the answer is 0 0.05, 0 0.1. This is the position, this is the velocity. So filter estimates position as 0.05. Okay. The sensor says 0.1. Now see the difference. The sensor says this is my position, 0.1 meter. The Kalman filter says no, it's 0 0.05. Right? Now, who is correct? We don't know. Right? If we have the true measurement, true position, right, we can do the comparison. Who is better, whether the sensor is better or the Kalman filter is better. So let's move forward. Now we can calculate now we have estimated something, but now we have to say, okay, what is the error covariance of that prediction? Okay, otherwise it's not meaningful. Remember, in the stochastic processes, when you say something as this is the value for this physical quantity, you also have to say what is the variance. Okay, otherwise it's meaningless. So now P1, that is the error covariance at k equals 1. This is the equation. Identity matrix minus k1, h1, p1 minus. So when you put the numbers in, you can do the calculation. This is P1, right? This is the error variance of the Kalman filter estimate. Let's move on to k equals 2. Now, this is the fully fledged iteration, right? Where we get the calculations of k1, right? A full use of those calculations into k2. First thing is the predicted value for the state at k2. So it is x2 minus. And we use the state transition, nothing else. We have the state transition matrix constant. And this is the previous estimate, right? We have already done it, 0 0.05, 0 0.1. The filters on estimate previous time index. So this is the predicted value for k equals 2, right? Now we have to correct it. This is like the draft, not final. What is the error covariance now? K equals 2, right? The draft value is given by this equation, same equation, right? And you put the numbers in, and this is your answer. 4.5332. This is different to what you had earlier, right? Because error covariance matrix changes, right, as you go. It's a dynamic thing. In this case, the state transition matrix is not changing, 1101. It's constant. But if it is changing time to time, that's not a problem. You can take it here and get going. So the predicted value, the draft value for error covariance here is 5.5, 5, 5, and 6. Okay. So when you add these two together. Now, what is the Kalman gain, right? Okay, equals to, this is the equation, put the numbers in, get the value. What is it? 0.9 to 0.83. So now the Kalman gain is yet another value, right? Another vector. So it's changing. Every step is a new value, new vector. Now you can use K2, right, to correct your estimate. What is the best estimate for the state? That is x2 hat given by this equation. So you put the numbers in again. The answer is minus 0.17, minus 0.19. So the filter says, Kalman filter says your position now at k equals 2 is 0.17 negative. And your velocity is 0.19. It is also negative. Okay. Now, if we go back to the question for the remaining parts, part 4, the first two random gas bursts post A0, 0.15 meters per second square, and A1 minus 0.8 meters per second square. Now you are given the actual accelerations, right? That cause this anomaly, right? The motion. And calculate the actual position of the spacecraft P1 and P2 at the first two sampling instance. So if you know the true values of the accelerometers, right? Because the gas bursts, right, as given over here, you can actually calculate the position, right? And then tabulate the actual position, measured position, and position estimated by a Kalman filter. So now you have true dynamics, true accelerations, right? You can measure position velocity, one thing. You have the sensor readings. You have the Kalman filter uh, estimates, right? You can compare these things. So this is that comparison. If you know the actual accelerations produced in the two instances, like K0 and K1. You can put these numbers in here for A0, right? As you can see it over here, 0.15, right? At K equals 1, your true position is 0.075, and you move on to T2, right? This time it is 0.8 minus, your position is minus 0.175, okay? Now you tabulate it. You can see it over here, K1 and K2, actual position, right? From these two equations, 0.075 and minus 0.175, like that. The true position of the spacecraft. And these are the two estimates of the Kalman field, 0.05 and minus 0.17. And these are the measurements, 0.1 minus 0.2, right? This is not anything conclusive, right? But to get an idea of how the Kalman filter behaves, right? Just by looking at it, at least you can say when you go to K equals 2, the actual position of the spacecraft and the Kalman filter are very close to each other. Minus 0.175, minus 0.17, right? So this is just to show you how the filter works. All right, any questions? Now, a lot of people want to use Kalman filters in MATLAB, okay? Now, after you have got an experience and manually calculating a couple of steps, how the Kalman filter works, right? Now, you can go straight to MATLAB and use the tools there to design a Kalman filter. So this slide shows you another example where you can use a Kalman filter in MATLAB. So this is my plant dynamics. X dot equals Ax plus Bu plus Qd plus 0V, right? I have taken everything that is possible, right? This is the state transition, Ax. This is the drive matrix because the controls. This is any disturbances. You can see it over here, the legend, right? D equals disturbances, V the sensor noise, Q the disturbances noise covariance matrix, R is the sensor noise variance. Okay. So these two equations, right, explain the whole state space model. Now, there are some zeros over here, you can see, because for the completeness we leave them there, right, without taking them away, but with a zero weight, which means it's not there. For example, the disturbances, right, it's not part of output matrix, right, generally, so it's 0 times d, but disturbances are part of the state transition, so they are there with some weightage matrix Q over here. And also the sensor noise is not part of the state dynamics, so it is 0 times V. But the sensor noise is very much a part of the output equation, right? So therefore you have R times V. So this is very clear to you, except for this 0 times V in the first equation and 0 times D in the second equation. Earlier, we had the dynamics, the unmodeled dynamics in the first equation. So Q times D is all right. And also we had the R times V, the second equation, output equation. That is also known. Only unknown is a new thing is over here, but you don't have to worry. they're all zeros. Okay, because in MATLAB you want to have everything is in matrix format, so you don't want to leave anything, do any prejudice and leave anything out. So you have the complete structure. Whenever where there is something which is not relevant, you put 0. Okay, right. So now you can write it down as two terms on the right hand side, right? Ax plus, you combine this bq0, right, as one matrix times udv as one column vector. Okay, for the equation 1 and also for the equation 2, you can see y equals cx plus d0r, right, times udv, right, udv, entire vector, control signal, disturbances, and sensor noise. Now this becomes a long vector, right? Say, if you look at the dimensions over here, a fourth order plant is used, right? Now, suppose you have a fourth order plant. So x dot is 4 by 1. There are 4 rows here. And you measure only one of them. So it is 1 by 1 output matrix. X is 4 by 1. So you can understand what is what is C. C is 1 by 4 because X is 4 by 1, right? So U is 1 by 1 because you have only one control signal. Right? So therefore D is 1 by 1. So likewise, I have written the sizes of the matrices. You can have a look at it later, leisurely, figure out how long the vectors are, how tall the columns are. Okay. This is a fourth order system. So X state vector is 4 by 1. All right. And there's only one control signal. So U is a scalar. It's a 1 by 1 matrix. So you have all these things you can calculate, right? I don't want to spend time on that. So when you have this concise format for the state space model, x dot equals ax plus b star u star. Now I use a star symbol to say that this is not the usual b vector, right? It is a compound vector, b star, and the size is 6 by 6. This is a big matrix. And u is not just u. Now it has a lot of components in it. So it's a 6 by 1 vector. Okay, all right. Because MATLAB needs this kind of structuring. Okay. Then I want to show you how you design the Kalman filter in MATLAB. It's simple command kf Kalman filter, right? It's not the command. It's, you can use anything for that, right? Kf is equal to LQR. There's this command in MATLAB, linear quadratic regulator, right? We'll do that later. Linear quadratic regulator is another controller like PID and compensators, but this is more optimal, right? For linear systems, you can design a linear quadratic regulator. If you know AC and also Q and R, are the process noise and the sensor noise covariances. So A dash, C dash meaning transpose of A and transpose of C, and the whole thing transpose. You generate a Kalman filter using this command, okay? And you can generate your system now with the Kalman filter, right? The system and the Kalman filter together as a combined system using this command, right? A system with KF using state space command. You generate the state space using these arguments, A minus KFC, then B AF, identity matrix of 4, size 4 by 4, and this is 0 times. So There's no logical explanation behind this. Once you know these matrices, right, and then combine them together in this format, you generate the state space model. Okay, and the LQR is linear quadratic regular. I said that it is an optimal controller. It optimizes the performance, right? Basically, it optimizes the error, reduce the error, and also reduce the energy, control effort. So it reduces both control effort and state deviation from the reference. Combine the two together, it generates the control signal. Okay, but it needs this matrix initially given, right? So for the four states, you have x1, x2, x3, x4, right? Say position, velocity, acceleration, jerk, for example, right? How important the position accuracy for you, right? You put it over here. I have put 100, which means I don't want to tolerate any error in position. This is velocity. How important is velocity accuracy? Right? When I use the Kalman filter to predict velocity, I say it is important, but not as important as the position. So I put 20 here, 20 here, and 30 here. This is jerk. For whatever reason, I said jerk. Accuracy of jerk is slightly more important than velocity and acceleration. So like that, this is a manual thing. You can put the numbers in, and MATLAB will generate the LQR. And also here WR means how costly is the control effort. Okay, if your control effort is not that costly, not that expensive, you can put a small value here. So I put 5 here. Look at 100 and this is 5. In this case, control effort is very cheap, like low cost petrol. You can buy, say, 20 rupees a liter. You don't worry to optimize it, right? But if it is expensive, then you put a bigger value over it. That is, you want to reduce it. Okay, the importance of the energy control effort. So with these two, you can use LQR, KLQR. This is the LQR controller, linear quadratic regulator, using LQR command, same LQR command as here. But this time you give it A, B, W, Q, WR. Okay. Here also remember the logical sequence. You have to give A and B matrices, that is the system and how we control it. And then W, Q, and WR. Okay. The cost weights for the 4 states and for the control signal. Then it generates LQR control. Now, what you do next is to prepare a Simulink model like this. What is that? So this is your augmented plant, A, B star, C, and D star. So A, B, C, D are already given in previous case, right? A, B, B star, D star, C, everything is already known, right? You generate this block in the Simulink and you generate this block, right? This is the system with the Kalman filter, right? Also as a block, right? In fact, the Kalman filter itself, Kalman filter block, all right? So then it produces X hat, that is the state estimate. And the linear quadratic regulator takes that estimate as feedback and generate the control signal, which goes over here. Okay. And this control signal is combined with other elements. You can see it over here, control signal and disturbances and noise, sensor noise, all these things combined together, the augmented system, right? Using a multiplex mux combined together, it goes to as U star to the plant. Okay, so when you have the U star to the plant, A plus B star U star, right? The plant operates. The same plant over here. Equation number 1 and number 2. So it produces YT. YT is the true output, which goes to the Kalman filter. And this is the control signal, which also goes to the Kalman filter. And Kalman filter knows about the plant. You can see it over here, A, B, etc. It knows it. And it produces an estimate. Okay. This YT is not available for measurement for whatever reason. Right? You don't have the full state vector. Because of that, you cannot feed it back and you cannot design a controller. But when you have the Kalman filter in place, right, with just one sensor reading, this YT is just one sensor reading. All other 3 states are not measured. This one signal goes over here to Kalman filter and it produces all 4. With all 4 states estimated, you can run the LQR. Otherwise, you can't have LQR. All right. Now, this is actually the Simulink model. I will share this model with you in the course website. You can download it and run it with the MATLAB code and then tweak it a little bit here and there, play with it and get some idea. Okay. So these are the process noise, right, and sensor noise combined together, right, and it goes to the augmented plant and produces output and goes to the Kalman filter and produces the 4 states. And this is the reference value we have given, right? So that the LQR will try to move the first state variable to that level, right? It's just a step signal. The first state variable x1 has to go to 1. And it produces its control signal, right? It goes as input to the plant. So it's operating like this, right? And in the same time, you have another LQR, right? Without the Kalman filter, right? So you get the augmented full output plant. Sorry, this is idealistic or theoretical part, right? You have this plant built in the Simulink, right? It produces the 4 states, full feedback. Whereas this one, only one feedback, right? The first element. And the Kalman filter estimates the other 3 altogether 4. So except for that difference, you have the same system running. Okay. For the comparison purpose, the true system with full state feedback, and the second one, only one state feedback, but the Kalman filter is there to estimate the other states. Now, this is the result you get. All right, you can see x1, the first state variable, and its estimate. Can you see it over here? The blue and red lines, they're very close to each other, right? This noisy signal is because of actually noise in the plant, because we have put the noisy over here, right? To see how the system works under noisy conditions. And this yellow one is the control signal. It goes like that, okay? The reference value is 1. Reference value is 1. and x1 is supposed to go to 1, but here you don't see it's going to 1, right? It stays below 1. This is x2, second state variable, third and fourth, the four uh, state vector. All of the states are actually reasonably estimated by the Kalman filter, right? That's one observation. Particularly the first one. The error of the first state variable, which means the difference between Kalman filter estimate and the true value, is very small. Okay. Now there's a question here. Y equals x1 doesn't climb to reference equals 1. Why? This is the reference signal. But the first state x1 doesn't go there. It stays below that. Can anybody tell why is it so? Okay, here what you see is the result of the LQR control with the Kalman filter, estimating the 4 states, state 1, 2, 3, and 4. And the first observation is Kalman filter predicts state 1 very closely, and state 2 and 3 and 4 are also reasonably good. But we observe one thing here, x1 variable, it doesn't go to 1. Okay, 1 is the set value. As you can see over here, we have given to the LQR input with a -1 offset in the first state variable, which means LQR will try to drive state variable to 0, but with this -1, it has to actually drive the state variable to 1, right? So 1 minus 1 is 0. So that's how we trick the LQR controller. But however, it doesn't go to 1. The question is why. Now, if you put various values for WR and see how the response changes. When you have WR20, you get this kind of response, WR10, this kind of response. WR equals 1, much better response. WR equals 0.1, very good response. Now, X1 goes to actual set value, that is 1. The reason is this WR is the cost of the control effort. If you have higher control effort, it's a high cost. Now, linear quadratic regulator has already optimized the control effort and the state error so that it has gone down to a certain minimum energy, minimum error design, so that it does not use much of the fuel, right, control when WR is high. That is why you cannot reach 1. If you want to reach the actual reference value, you need to put energy. But now, energy is so expensive, don't want to put that much energy. So you live with some error. That's what happens over here. But when WR is equal to 0.1, cost of fuel is very cheap, very low. So you can use as much fuel as you wish to reach the zero accuracy. Okay, zero error rather. So that's why what you see in last photograph here, figure, when WR is 0.1, very cheap fuel, you use as much energy as you wish, as needed to get that level X1 raise up to 1. And whatever remaining changes up and down is because of noise. All right, so that's end of the LQR based control using the Kalman filter. All right, and next day we'll discuss about extended Kalman filter.